Hello everyone, welcome to today's webinar, Compilation of Julia Code for Deployment in Model-Based Engineering Workflows. Today, we'll explore how Julia's advanced compiler technology enhances scientific computing, embedded systems, and real-time simulation workflows, all without relying on C code. Our presenter, Fredrik Bagge-Carlsen, will share insights and real-world case studies demonstrating these advancements. Thank you for joining us, and let's dive in. With this, over to you, Fredrik.
Thank you, Sanjeev. All right, welcome. I'm happy to see so many of you have joined the webinar today. As Sanjeev said, today we'll talk about interesting ways that we can compile Julia and maybe deploy Julia. That today, the topic of today's webinar is kind of like a status update in Julia land. So it doesn't necessarily relate directly to any of our products at JuliaHub. Instead, it's about fundamental technology related to the Julia compiler. So today we will talk very briefly about what is Julia, and I assume that most of you know that. But the introduction will still make sense in the context of what we will talk about today. And we will talk about the standard Julia compilation pipeline, and I don't want you to freak out about this. We're not going to require any deep compiler knowledge here. We will just briefly talk about how it works today. And then we'll talk about how it has historically worked if we want to ahead of time compile Julia. So compile a binary and maybe ship that to someone else. Then we will pivot over to how it looks now and in the near future. And this is kind of the thing we're actually interested in here in today's webinar. We will show two demos of this capability. We will produce one executable, so a binary that someone can execute on a different computer. And the demo example here is state estimation. And then we will compile one shared library, and that will be a shared library of a PID controller. So we will take a Julia package, existing Julia package that implements PID controllers, and then we will make a shared library out of that we can call from, for example, a C program. And then we will spend some time discussing current limitations. I said that this is to be viewed as a status update. So there are current limitations, and we will talk about those also. So first, the Julia programming language. It is a programming language. We have some example Julia code here on the left. We can define structures. So here we have a struct circle, and it contains just a floating point value. So this behaves, looks, and feels very similar to a struct in C. And that turns out will be very convenient when we want to interface C programs. We can define a function area. It takes an argument that has a type circle, and then it performs some computation. All right, so here we have said that C, the argument is of type circle. All right, and then we can define another geometric shape, a rectangle, and we can define a new method of the function area that takes a rectangle. It performs a different computation. So here we have two instances of the same function defined. What we're actually defining here is two different methods. And what distinguishes them is the type of the signature here. That the argument has a different type in the two different cases. We can create an array of different shapes. So here we have an array of 3 shapes. And we can broadcast the function area over all these shapes. And now we see, even though we had different types of the elements in the array, we got answers for all of them. Okay, so that's very, very brief introduction to Julia. We can also define a function here where function f that takes an argument x, but we don't say what the type x is. We just perform some computation here using x. So we square it, and then we add x also. And then we can call this function with a few different types as input arguments. So if we call it with an integer number 2 here, we get an integer back. The result of that is 6. If we call it with a floating point value, the result is another floating point value. And we can call it with a complex number here, so 2 plus the imaginary unit, and we get a complex result. We can also actually call it with a matrix, right? And we get a matrix back because we can square matrices and we can add the matrices to each other and so on. And here I show that we can also load a package forward diff that provides dual numbers. So a dual number is used for automatic differentiation. And if we pass that number into the function, we get the result and the derivative of the result. So that's very convenient. So Julia allows us to define a function that takes some argument, and we don't have to specify what type it is, even though we can specify what type it is if we want to specialize on the type. But it allows us to pass any kind of type in there as long as these operations that are used inside of the function are defined. And that will turn out to be very convenient as well. But what happens underneath the hood? So we can ask the compiler what it produces for these different function calls. So if I called f with an integer, we see that I get, and this is now assembly instructions. I don't expect you to understand the assembly. I will just point out that the compiler emits two instructions here. We multiply two integers, I mul, q, I think q stands for quad, the size of the integer, and then we add two integers. Okay, but if we call function f with a floating point value, we now see that the compiler emits different instructions. So the Julia compiler will compile different machine code for the function f depending on what type of the input argument we call it with. And here we see if we call with a complex number, it produces slightly more instructions because these are now two tuples, but it nevertheless produces machine code. All right, so the normal Julia compiler pipeline, people jokingly perhaps call Julia a just ahead of time compiled language. And we will see what that means. So the Julia compiler starts like most other compilers with some source code. It performs a number of steps in Julia, namely type inference and some Julia level optimization. So type inference is the compiler trying to figure out if A has a certain type, what will be the type of B and what will be the type of the result of the sign of B and so on. Then eventually Julia calls LLVM, and LLVM is kind of the low-level compiler that is responsible for generating the actual machine code. And the LLVM performs its optimization, and then in the end we have a native code that executes on the processor. So here we have another function, Julia function, and this is a tricky function. It takes an argument A, and then if we look at the first line in the function body here, it says that if A is greater than 0, then B is the integer 1. Otherwise, B is the matrix, the random matrix 2 by 2 matrix here. So if we just know the type of A, we don't actually know, that's not enough to know what type B will have, because that depends on a runtime value, right? So the compiler can't possibly know the type of B. And then if it doesn't know the type of B, then it doesn't know which method of sign to call, because B might be either a matrix or an integer. So what version of sign should we call? Okay, so that's obviously a problem. Nevertheless, Julia accepts us calling here. If we call with a negative value, we get a matrix back. And if we pass a positive value, we get a number back. So this function worked, even though we had kind of different types as a result. But what happens here is that Julia allows us to execute this until we get to this point. And then it realizes it doesn't know what type B is until runtime. And then at runtime, it will invoke the compiler again when we know the type and compile the corresponding version of sign and then dispatch to that. So this is the way Julia works if you install Julia and use it normally. But this might be problematic when we want to compile a binary, and we will talk about why that is soon. So historically, if we wanted to compile a binary of Julia code and distribute that, maybe I want to send my program to you so you can run it. I could choose to either distribute the source code, so the raw Julia code, or I could package everything into a huge binary. And when I say everything, I mean the package and all application source code, any package I depend on, maybe I would have to put in there, all the compiled code and the Julia compiler itself and the LLVM compiler and the Julia runtime. Okay, and that has a number of benefits. If I do that, I can use all language features, and you can also use all language features on your side. And it's nice and self-contained. It contains everything that you might possibly want to use. The drawbacks is, of course, if I send you source code, then you need to have Julia installed on your machine. So that's not a huge problem. You can install Julia on your machine, but it's still an additional step that we might not always want. And it's not guaranteed to be fully ahead of time compiled. So the compiler is still inside of this huge binary I sent you, and you might execute code that requires the compiler to perform compilation online. And that's nice in the sense that it works, but it's sometimes bad in the sense that it introduces some latency because the compiler takes some time to compile code, right? And in certain cases, that latency is not great. For example, if we have a real-time system, that might not be acceptable. Another downside is that the generated binary tend to be very large. It might be over a gigabyte large because it contains the Julia compiler and a whole lot of source code that we might not need. And it's not always relocatable, so it might depend on some paths that you have on your machine that is not the same on a different machine and so on. But nevertheless, this has existed for a long time and will continue to exist, and it's quite nice to use, but it's not always the solution we're looking for. So how does this look now and in the near future? All right, so the idea here is that the Julia compiler can analyze a program and figure out what parts of the code is reachable from an entry point. And everything that is not reachable from an entry point, we can essentially remove that from the binary. And in Julia land, that is called trimming. So we have a new compile time feature that is called trimming that will essentially reduce the size of the binary produced by the Julia compiler. And then the idea is that if the compiler encounters any code in your program that is fundamentally uncompilable ahead of time, then you will get an error. So examples of that is if you call eval. Eval will evaluate and compile code at runtime. So that's obviously not acceptable if you want to compile ahead of time. And it's not acceptable if the types in your program are completely unknown. So if type inference fails, saying that I have no idea what type this variable has. And if you then try to make use of that variable, we don't know what code to call until runtime. So that's not acceptable either. And we have benefits and drawbacks of this workflow as well. So a benefit is that it may produce significantly smaller binaries. So I say here smallish binaries. Hello world is about 900 kilobytes at the time of this webinar. So that might go down further in the future. That's significantly smaller than several gigabytes, but it's still significantly bigger than Hello World in C, for example. But this has now reached a level where this is small enough to deploy on quite small platforms. It also guarantees that every code that can potentially be reached from an entry point is compiled ahead of time. So you will have no compiler latency while you execute this binary. And another benefit is that most language features are intact. So you don't have any runtime eval and no unbounded dispatch like I mentioned before. All right, but we still have a number of limitations. So this is not yet released. That's why I say it's a status update. The demos I showed today will be running on the nightly version of Julia. So not a version you can install through the regular channels. There is no easy cross-compilation, so I can easily compile for my own machine, and you can run it on a very similar machine, but I can't easily compile for example, a Raspberry Pi using my desktop PC. I say not easy, it's not impossible, but it's currently not easy. And the compiled binary is not fully self-contained yet, so it still links to libjulia, for example, which is something to take into consideration. So that makes the footprint slightly larger, but work is being done to lift that limitation as well. All right, so if we go back to this tricky function foo, where we don't know the type of B at compile time, will that be okay under this new compilation workflow? And the answer is actually yes, it is okay. We can ask the compiler what it thinks about the types in this little function. And here I call function foo with an integer, and I have a macro ahead of it, or in front of it here, code warn type. It asks the compiler, what types have you inferred in this program, and print in nice colors if there is anything that you don't like. Okay. So we see a number of prints in orange. Okay, so the compiler can show something in red also. That means it really doesn't like it. But here it has shown in orange, and it shows that B is either an integer or a matrix. All right, but it knows that it has to be one of those two. So that means that when we call sign of B, we have to call either integer sign or matrix sign. It can't be anything else. All right, and that's enough because then the compiler has a bounded number of methods of sign it has to compile and put in the binary. So it doesn't need to compile a sign for dual numbers because it knows that a B can't possibly be a dual number. All right, so this turns out it was actually okay, even though it seems like a very nasty situation for the compiler to be in. Right, so now we will show two very brief demos of this. And I said that in one demo, we will compile an executable. So that's like a file you can launch and it does something. And that demo will perform state estimation. So if you're familiar with state estimation, it's in a dynamical system. We might want to infer the state of the system given noisy measurements. And the noisy measurements are not always covering all the state and so on. So that's a kind of a nice inference problem. And for that, we will make use of an equation-based modeling language called Modeling Toolkit. Then we will use a state estimator from a Julia package, already existing Julia package. And then we will, our executable will load some data from a file and perform filtering over that data. And the second demo, we will compile a shared library. So on Linux, that would be an SO file. On Windows, it will be a DLL file. And it will contain PID controller functionality that we might want to call from a C program. And we will do that also in the demo. All right, so the first demo with the model-based state estimation. So I will use a modeling toolkit model. I will not go into details on either modeling toolkit or the modeling of the system in this webinar. I will just show the code that defines the model. The model is of a continuously stirred tank reactor. So we have a tank with a kind of a propeller in there that mixes its contents. And inside the reactor is some chemical reaction taking place. So two different reactants are reacting and combining some desired outcome. And that produces heat. And to mitigate the heat production, we have a cooling jacket around the tank reactor that can cool. And when the reaction takes place, it generates heat, I said, and then that makes the reaction go faster. So that's kind of an unstable system. So it's an interesting system from a control perspective. But today we will perform state estimations. We will try to use measurements of the inputs and the outputs of this system to infer the internal state here. And we'll combine Modeling Toolkit here with an off-the-shelf Julia library for state estimation and package those two together into an executable. And if you're interested in replicating this experiment, the source code is available in this link or this dinosaur QR code here. So here we have the Modeling Toolkit model that defines the dynamics for this system. It defines a number of variables and a number of intermediate expressions and then a number of equations. So we have 4 equations here. We have 4 state variables and we have 2 input variables. And then I instantiate the model as a Julia object. I specify what my inputs are, and then I call a function in Modeling Toolkit, generate control function. So this will generate a Julia function for the right-hand side, essentially, of this dynamical system. And then I will package this code into a Julia file that I might load when I perform my compilation. Then I have a Julia module here I call state estimator. And this is the module that I will compile into the binary. That makes use of a package for state estimation called low-level particle filters. And it also makes use of a number of lower-level Julia utility packages. I define a number of variables. So we have a sample time. This is the interval between samples. We have an initial state, an initial control input, and some parameters. The parameters here are nothing. I define how the measurement is being generated based on the state. So we assume here that we can measure the full state. Then I include the dynamics that I generated in the previous slide with the Modeling Toolkit. I discretize that dynamic, so that's a continuous time ordinary differential equation, and I discretize that with an RK4 method. So this is a commonplace integrator, and now I have a discrete time version of that dynamics. And then I specify a number of parameters for the state estimator. So it's a nonlinear version of a Kalman filter. So it takes covariance matrices for the noise driving the dynamics and the measurement noise and so on. And then I package that into a Julia object called an uncentered Kalman filter here. And this is what I will use for the filtering. And then in my main function, so this is a main function similar to a C main function. I annotate that saying that this is C callable. So that's an entry point. This is Julia's way of specifying that this is an entry point to this binary. I print a status update saying that, yes, the program has started, and then load some data from file here. So I read two files, data Y and data U. And this is binary files, so I reinterpret that into the correct data type on the Julia side. And then I call this function forward trajectory, which essentially performs the state estimation in a batch. So these variables U and Y are now vectors of inputs and outputs. And then to see that I got something reasonable, I print the estimated log likelihood of this data sequence. And then I return 0, hopefully, indicating that this program terminated successfully. And if I run this, if I compile this, I get the binary size, at least at the time when I produced these slides, the binary was 3.5 megabytes large, and the runtime was about 27 milliseconds from the terminal. And of that time, the filtering here, the kind of the main business logic of this program, it took 62 microseconds. So there is some startup overhead where the Julia runtime is loaded and so on that increases this to 27 milliseconds. But it's still reasonably large. And I will see if I can perform this compilation here live during the webinar. So this is always a bit tricky, live demos, but I have prepared, so hopefully it works. So here I show the full Julia command that performs this actual compilation. So I invoke Julia. I tell Julia that I want to use the 1.12 nightly version. So this is not the released Julia version, as I said. This is, think of it as an before alpha version. I specify that I want to use a particular project environment. So this is so Julia knows which versions of packages I want to use and so on. And the project environment is from the repository I linked to before. Then I tell Julia, invoke the Julia C file. So that's the Julia C compiler that contains the trimming functionality. I tell it specify and generate an output executable. And I want that executable to be called Julia demo. I want the compiler to use its trimming mode. And I say that I allow unsafe behavior, but I want you to warn me about it. I explicitly indicate here that, yes, I know that this functionality is experimental. So this is a flag that the Julia compiler forces me to use to acknowledge that this functionality is experimental. So don't expect it to work 100% and expect it to maybe break in the future and change the way it behaves and so on. But I am willing to accept that. And so I give this flag. And then finally, I provide the script to that I actually want to compile. All right, so I will hit enter here, and this will now take a little while. I expect it to take about 20 seconds or something like that. And what is happening now is that Julia is essentially loading the script that I showed in the previous slide. And it's performing compile time analysis. So it's not running the script. It's essentially doing abstract interpretation to figure out exactly what code can be run, can be hit from your entry point, so the main function, and removing everything that cannot be reached. And it will issue any errors and so on if it encounters anything it can't compile. So it has finished here. It printed a number of integers here in the terminal. Those are integers that I explicitly asked it to print out to give some kind of continuous status update. It prints a number of warnings. So those warnings are currently benign and we can ignore them. And hopefully a future version of this will make sure that they are not printed. But now we can see if this produced a binary. And it did here, Julia C demo. It is 3.9 megabytes large at the moment, and it was produced right now. And now hopefully we can also run that binary. And it worked. It gave me the status update that the program is running, read the data, and it performed the filtering, and it got a certain log likelihood number here. Okay, so we can time that to see if it works as fast as I said before. And it's about 36 milliseconds. So it appears as if the demo worked out okay. All right. The next demo, this is in case the demo didn't work, I showed how it's supposed to look here. The next demo, we're going to compile a shared library. And here we will demonstrate that we can take an existing Julia package. In this case, the Julia package contains an implementation of a PID controller. And then we can produce an executable, or rather a shared library that exposes the function in this library such that they can be called from a C program. And this demo is also available on this link here or on this QR code. So here we see the little script that I will compile. I create a global instance of a PID controller, and I give it some arbitrary starting parameters, 111. And the reason is that I have functions that can change those parameters. And the interesting thing is actually what's going on in these functions. So in this package, discrete PIDs, we have a function called calculate control. It takes the current reference and measurement signal and calculates the control output. This function is not C callable, so it's not an entry point that can be called from C. So what I do here is I've wrapped this function in a function with the same name that is C callable. And this now tells Julia that when you create a shared object file, I want you to include an entry point with this function name here. And as you can see, I don't include this PID controller in the input signature of the wrapper function. Instead, I make use of this global instance of a PID controller. And that's just to simplify the interface on the C side slightly so that I don't have to instantiate the Julia struct on the C side. Then I do the same thing for a number of other functions in this package. So there is one function that modifies the K, the proportional gain, the integral time constant, and the derivative time, and so on. And I can also reset the state of the PID controller. And then to make use of this from the C side, I specify a path to my shared object file. And then I do a dynamic link, dynamic library open here. So I open the SO file that I compiled. And then I need to instantiate, or rather initiate, the Julia runtime. So this is one step that hopefully will not be required in the future. But at the time of this webinar, it is required. So I need to issue this function call here that says that I now instantiate, or rather initialize, the Julia runtime in case the compiled library is requesting any function from the runtime. And then I have a very simple test program here that just calculates a number of control signals. So I specify a reference, a measurement, and a feed forward signal, and I pass those into the calculate control function here. So this is now C code that is calling the Julia function, calculate control, and I print the result and so on. And then I call a few of the other functions in the shared object file just to test that it works. All right, to compile this, I use GCC here. I will not do this live, just indicate how I compile it when I run it. GCC, I pass my source file, the C source file, and then I pass some paths to make sure that it knows where to find the Julia runtime, because it needs to link against that. All right. Can I do this on a Raspberry Pi? Can I compile code such that it runs on a platform like a Raspberry Pi? And the answer is yes, I can perform exactly this workflow on a Raspberry Pi. So Raspberry Pi, you can install Julia there, launch Julia, and run Julia like on any other computer. including using this compiler. If I do that, and I have done that on a Raspberry Pi 5, if I'm not mistaken, the binary runtime is about 4 times slower on the Raspberry Pi. So that's perhaps expected. It's a significantly slower platform than my desktop PC that I'm running this on. But nevertheless, it works and it's reasonably fast. There is currently no real first-class support for cross-compilation. So that is something that is work in progress, and hopefully within a year or so we will have that. But something that is currently an option in some situations is to use emulation to perform cross-compilation. So I can, on my desktop PC, run an emulator for the platform I want to compile on and perform the compilation in there. And that has been successfully demonstrated for a number of platforms. All right, more current limitations. I have alluded to several limitations already, but there are more, and I want everyone to be aware of those. And at the same time, I don't want to scare anyone away. So all of these limitations are being worked on and being addressed as we speak. But currently, the landscape looks more or less like this. The first point is that the Julia runtime is required. And that means that it only works on quote-unquote supported platforms. So that means that if you're running a traditional operating system like Linux, Windows, or Mac OS, then you're probably good to go. And if you are on a processor like x86-64 or an ARM version 8 processor, then there should be no problems. If you are on an ARM v7 or on a RISC-V processor, it might work. So Julia has been demonstrated to work, or it has worked at one point in time, but it might not be completely straightforward. All right, and if you're on an esoteric real-time OS, currently it will probably not work. At least it will not be easy to make it work. And then I show here, so this emoji here is a wizard. I say, can you run this on an Arduino? Can I produce a Julia binary that runs on an Arduino? And the answer is surprisingly yes, but under very limited circumstances, and you have to be a real wizard to make that work. But it is a work in progress to make stuff like this actually work and make it feel more first class. But currently, it's very much in the, let's say, work in progress. Another limitation is that the runtime itself is not trimmed. So we trim the user code, but we don't trim the runtime. So the runtime is still fairly large. I believe it's on the order of 40 megabytes, something like that, 30 to 50, I guess. And those need to be linked against those shared libraries. So the total footprint in terms of the size is currently has a lower bound around the size of the runtime. Another limitation is, of course, that it's not yet released. So you can't just make use of this in a released version of Julia today. And that also means that it's not fully stable. So if you if you try to reproduce my demos, you might run into problem if you use a slightly different nightly version of Julia and so on. So I want you to be prepared for that. I mentioned cross-compilation limitations already, so I will not dive into that more, but keep in mind that it's a limitation. And finally, I want to say once again that all of these limitations are being worked on as we speak. And it's very much in our interest to lift more or less all of these limitations as soon as possible, more or less. So finally, should you make use of this today? And I try to be a bit funny here and ask if you're a Julia hacker. And if you are, then the answer is maybe. And if you are not, then the answer is most definitely no. You should not use this today. You should wait until it's released. Otherwise, you will have headaches. But I recognize that there are a lot of Julia hackers out there. And you might be very interested in actually trying this already today. So that certainly is possible. All right, so for a summary of this webinar, we have seen how we can today make use of Julia in an ahead-of-time compilation workflow. And we can compile Julia to a small-ish binary. It's not small as C, but it's certainly small with the historical Julia standards. Most features of Julia are intact while making use of this, which is a nice thing. There are restrictions, of course, around too much dynamic behavior, so we cannot use runtime eval or have unbounded dispatch. So the compiler must be able to infer types in your program. It's not yet released in a stable Julia version. So the upcoming version 1.12 has gone through feature freeze a few months ago. So hopefully it will be released in a not too distant future. And if you're interested in FMUs, so FMU functional markup units, that's a particular form of a binary that is used in simulation of dynamical systems. We have been able to produce such FMUs before, and they have had the traditional Julia binary issue that the file size is very large. With this new functionality, we can produce significantly smaller FMUs. But this is also slightly work in progress. We have demonstrated that it works, but it's not yet convenient for you to use. So expect that to change when this version 1.12 is released. All right, and finally, if you want to reach out, if you have any questions regarding either Julia Sim or any of the code generation capabilities, or you want support with code generation or deployment of Julia code, then be sure to reach out to this email address or this QR code here for a web form. And with that, I would like to thank you for your attention during today's webinar, and I would be happy to take any questions. And I see that we already have one question. I will read it out loud for the rest of the participants. There is a question regarding the pros and cons for source code distribution or binary or both. All right, so let me clarify that. If I distribute source code, that means that the recipient must have Julia installed. All right, if they have that, they have all features of the language available. And the file size is also very small, right? It's the size of the source code that I distribute. So that's very nice. But if I want to distribute a binary, so a package that includes everything that someone can just execute, then I have all the other pros and cons. So the file size and so on. I hope that clarifies. Let's see. There is a long question here. I will read it and then repeat it. Is it possible, or does it make sense to perform software in the loop using binary with Julia? So that is certainly sensible. And in fact, I believe we have a webinar scheduled in just a few days that will demonstrate exactly that. So if you tune into our webinar page on JuliaHub.com, you should be able to find a webinar that is on the top of the page that advertises more or less exactly that workflow. So I'm happy to share that. There is a question: how will this work with CUDA and other similar GPU programming environments? I see I have my colleague Cody here. I hope Cody can answer that question. I will defer to Cody. Are you able to speak, Cody?
Yeah, I can cover that one. So the CUDA support we haven't looked into specifically yet. That would require additional support in GPU compiler we don't have yet today. I don't think that there is any tremendous fundamental challenges to making that work, but we haven't planned it out yet on the roadmap. So that would be another, I think, to-do item to consider for the future. But certainly you can imagine an application like that would, I mean, GPU compiler already does this kind of static compilation for the GPU. So the real challenge there is just weaving that code together so that it can all be emitted in the same binary. So eventually we do hope to support that, but not yet today.
All right, excellent, thank you. And there is a question whether this is a plan to replace package compiler. And,
I think the answer there is that we're hoping this is going to essentially be a replacement for the workflow internally to package compiler. Very likely a lot of this functionality that you've seen here is a very internal version of something that will be eventually released via the package compiler interface. So one day you'll go in to an updated version of package compiler and you'll be able to compile a small binary with trimming enabled. And that will use all the same technologies that Frederick showed off today. So rather than replacing package compiler, the idea here is to give package compiler a lot of extra power to emit smaller binaries rather than just the one mode of operation that it's had up until now, which is what Frederick covered at the beginning, where you emit a giant binary with LLVM and the Julia compiler included. This would be a much smaller binary. Instead of being 500 to 600 megabytes, it's going to be on the scale of what Frederick's talking about. So ideally 5 to 10 megabytes for your user code, and then about 50 megabytes for the runtime until we can trim that more aggressively. And most of that runtime overhead, just for the record, is related to linear algebra support and high-speed BLAS routines and that kind of thing.
All right, cool. Thank you. And then there is a question, best guess when Julia version 1.12 will be released. And I believe that all guesses there are bad guesses historically. I believe the feature freeze has taken place a long time ago. And I believe the work is currently being done to iron out all the problems to make sure that it builds on all supported platforms and so on. I don't know, Cody, if you have any further insight.
Yeah, I mean, I agree with you. These things are kind of fundamentally chaotic, but the target, ideally, we'd really like to have a good version, a stable version of 1.12 out in time for JuliaCon. So somewhere on the order of the next 5 or 6 months, we'd really like to have that in a good spot and either officially released or very close to it.
Cool. And regarding multi-threaded and multi-process applications, can I use Julia C and the trimming capability with such a program?
Yeah, you absolutely can. So we support multi-threaded entry points. You can call Julia code for multiple different C threads by default. All that should just work pretty much out of the box. Obviously, the Julia code you write itself needs to be written with multi-threading in mind, because Julia is not. You can easily write code that, for example, accesses mutable data for multiple threads at once, and that can create problems in your Julia code in the same way it does in C code. But as long as you're using thread-safe constructs in your Julia code, then the runtime and the export all support that. So multi-threaded code are supported just fine.
All right, very good. Thank you. And the next question is, I saw that compilation was performed using version 1.12 nightly. How far back in Julia version will there be support for this? And I believe that Julia version 1.12 will be required to make use of this. You will not be able to use any older Julia version than that.
Yeah, that's right. Unfortunately, we're not going to be able to backport this functionality, so it's going to be 1.12 and onward.
Yep. The next question is whether or not trimming is mandatory. And I believe that no, you don't have to perform trimming, and then you're in the situation that the package compiler currently provides.
Yeah, that's exactly right. So if you disable trimming, you'll basically get the old experience of package compiler, and you'll end up with several extra 100 megabytes to keep the Julia compiler LLVM and bring that all along with you. So trimming is only mandatory if you want to get rid of all that extra weight.
All right, very good. The final question so far is, would the PID controller work on UPC UA? And there I have to ask what those abbreviations are for, because I'm not familiar with them. It's UPC is a communication protocol. In that case, I don't actually know. I don't have any insight into that. If you can operate over OPC through a regular Julia program, I believe there should be no problem as long as that interface is type stable, as I showed during the webinar. If the Julia compiler can infer the type, in particular, I can imagine that you have incoming messages. As long as the Julia compiler knows what type will result from the message over the communication protocol, you should be able to make use of this, I believe. But it very much depends on the interface package. Yeah.
The only other note I would add there is that you can always, I mean, depending on how you architect this, you can always implement the communication protocol on the C side, and then leave just the controller implemented in Julia, and then call into the Julia code as a library. In that case, that should work just fine too. I think the main constraints to keep in mind here, usually when folks ask about communication protocols, they start thinking about real-time operating systems and embedded platforms. So the main constraints to be aware of there are probably the slide from just before this that Frederick was showing, that talks about how we don't yet have good real-time operating system support. But as long as you're running within a proper operating system like Linux, and you can call in from some C code, then absolutely you can hook this up to whatever communication protocol you might like. We don't have out-of-box support for that, but you can make it work.
Cool. We have more questions now. What about alternative BLAS libraries? Can I use this with MKL?
Yeah, that's a great question. You can use it with MKL. We're not yet smart enough to actually get rid of the original BLAS because you're using MKL instead. So unfortunately, we'll pay some size cost, although I think MKL is a couple of gigabytes when I last checked, or at least one. So it's quite large compared to anything else here. So the artifact size is really heavy for MKL. But if you want to support MKL, absolutely you can do that.
All right, cool. I believe that was the last question. So if nothing else drops in, I would like to thank all participants and also Cody for dropping in and sharing your answers. All right. Okay, actually one more question appeared. Can I provide input parameters similar to the old version and have the compiler infer data types? Yes, you can do that. I believe you need to specify the type on entry points. But apart from entry points, the entire Julia compilation pipeline works the same. So how should I put this? The Julia compiler will make use of a type inference as normal. And as long as type inference succeeds, you're good to go. If type inference fails, you will get a compilation error, in this case saying that a dynamic call was detected, and it will tell you which line in the source code and what the particular error is, so that you can fix that. But otherwise, there should be no problem. In particular, the function f I showed that didn't specify what type the input argument had. That would be perfectly okay. The issue arises if at the call site where f is called, if the compiler doesn't know what type x has, then the compiler doesn't know which version of f to compile, and that's not okay. It must know that. But if it does know that, everything is green light.
Yeah, I don't know if you want to show the example with @callable one more time. That might be useful to point out that those type those type parameters there are required. So that's the way to provide the type of input parameters.
Yes. So here I say that the input is of type T. Unfortunately, where the line in the code where I specify T is actually not shown. But here I say that T is float 64. So it's in C language, that's called double. So K is a double, R is a double, Y is a double, and the return of this function is a void. This function returns a double. So this is the Julia syntax to annotate what the type of the return of the function is. So here, since this is an entry point, I need to specify those types. But in this inner function here, calculate control inside this library, the type of these arguments is not specified, for example. So this accepts if T had been 32-bit float, that would still be okay. And if T had been a fixed point number, that would also be okay. So you have that flexibility of Julia intact. Okay, more questions have arisen. Are you aware of some examples of algorithmically differentiated code that were statically compiled? And the answer is yes. So in my state estimation demo, I made use of an uncentered Kalman filter. But you can run that demo with an extended Kalman filter also. And the extended Kalman filter performs automatic differentiation to compute the state Jacobian and the input Jacobian. So the details of the extended Kalman filter I will leave out, but it requires Jacobian computations. And historically, when people use extended Kalman filters, they rely on either manually hand-coded Jacobians or they make use of finite difference perturbation to compute those Jacobians. And we can make use of that also, but by default, we make use of automatic differentiation to compute those for you, so that you will have fast and accurate Jacobian computation for free, essentially. All right. More questions? All right. Thank you, Cody. Thank you, participants. Thank you, Sanjeev. Sanjeev, you have any closing remarks?
Yep. So we will share the video recording with all the participants via an email, and we'll also put it up on our website in case you want to watch it later. Apart from that, as Frederick mentioned, we have other webinars coming up. If you go to the our website, in the event section, you will be able to see the upcoming webinars. You can register for them as well. And in case you have any queries, do write into us at the email ID that Frederick provided, and we'll get back to you at the earliest. Thank you, everyone. Thank you, Frederick.
Thank you.
Have a good
You
day.
all.
Bye.